In the previous video, we showed you an example that a matrix can have a finite number of eigenvalues and eigenvectors. However, in many cases, it can be more complicated. In the first example in this video today, we will look at a matrix that has infinite number of eigenvectors. Let's write down the matrix A. The question asks you to calculate the eigenvectors and eigenvalues. From the previous video, we learned that we need to construct a new matrix using the diagonal entries minus the eigenvalue. Let's write down the new matrix. What we need to do, according to the Cramer's theorem, is the determinant of this new matrix should equal to 0. This is a 3x3 matrix. I will not go through the details how to calculate the determinant of 3x3 matrix. I'll write down the expression. From this, we can solve lambda, the eigenvalues. There are 3 eigenvalues, or to be more precise, there are 2 distinct eigenvalues, 5 and minus 3. Next, let's calculate the eigenvectors that correspond to the eigenvalues for lambda is equal to 5. When we substitute lambda is equal to 5 into the above matrix, we'll have a new matrix. To solve x1, x2, and x3, the eigenvectors, we need to reduce the matrix. If you perform the Gauss elimination, you can get a new matrix. If you look at the new matrix, after Gauss elimination, all the entries in the third row are zeros. That tells us the 3 equations are linearly dependent. In this case, we have 3 unknowns, but only 2 equations. So you do not have a single set of eigenvectors. There's one thing I want to draw your attention to. Although we have infinite number of eigenvectors, x1, x2, and x3, they are not random numbers. These 3 values still have to satisfy the 2 linear equations identified by the first 2 rows of the matrix. If you really want to get one set of eigenvectors, you can assume x1 to be any value like 1 or minus 1 or 2 or 3, then calculate x2 and x3. Then the eigenvector calculated must be one of the infinite number of eigenvectors for this matrix. In the next example, you will see that you can have complex eigenvalues and eigenvectors from a real matrix. For matrix A, it has the following entries: 0, 1, minus 1, and 0. Let's look at the eigenvalue. Again, from what we have learned before, what we need to do is to construct a new matrix where the diagonal is the entry minus lambda, and calculate the determinant of that new matrix. If we rewrite it, we're getting minus lambda times minus lambda minus 1 multiplied by minus 1. And we need to set it into 0. Minus lambda, that's lambda square. And 1 times minus 1 is minus 1. The minus is plus. That gives us lambda square is equal to minus 1. Then there are 2 solutions for lambda. Lambda 1 is equal to I, and lambda 2 is equal to minus I. In this video, you have seen some less common examples of eigenvalues and eigenvector calculations. In the next video, we'll show you a couple examples how we can use eigenvalues and eigenvectors to solve engineering problems.